Good morning, everyone. My name is Ginni Grover. I'm working at Intel Labs. Today, I'm going to talk about integral displays and their ability to provide correct retinal blur or depth blur for depth perception. So my talk is divided in 4 sections. First, I'll talk about the image formation model that I've used in these study of integral displays. Second, I'll talk about the important depth cue used in human vision called retinal blur or depth blur, which stimulates accommodation. And then third, I'll talk about the simulation method which I've used to study these in-focus and out-of-focus spots, and then finally summarize with results. So integral displays are a form of light field displays which have been studied very well for a very long time now. First proposed, they are derived from integral imaging, which was proposed about 100 years ago. A simple schematic, excuse me. So how do I turn on the laser pointer? Okay, yeah. So here is a simple schematic of an integral displays. It consists of a screen covered by small lenses on the top called lenslet array. The image displayed on this screen is a special composited image made of these small elemental images. So when the viewer stands in front of these display, they see a 3D scene. So here is an example. As the viewer moves their head, they see different views, so they have a parallax as they move their head or for their different eyes. These displays have many different parameters which can be tuned, which define the 3 most important characteristics of these displays. One is the depth of field, that is the depth within which the viewer can see a 3D scene. The second is the eye box width or the viewing zone, this width where the viewer can move their head, and then third is image spatial resolution. Many different modifications of these integral displays have been proposed and studied, but I am going to focus on one specific case here where the spacing between the screen and the lenslet is equal to the focal length of the lenses used. Why I'm interested in these is because in this, the depth which the viewer perceives is equally divided in the front as well as the back. One of the cases is when the spacing is such that the entire depth of the scene is in the front of the display or in the back of the display. But I'm not talking about, this method can be applied to those techniques, but I'm not discussing them here. So a few words about depth perception in humans. So they can be broadly, the depth cues, how we see 3D, can be broadly classified into 2. Binocular, we all just saw an example of using disparity and parallax. And the monocular cue is this important depth blur leading to accommodation of the eye. Accommodation of the eye is simply focusing ability of the eye, where eye is can focus at different depths and the scene comes in and out of focus. 3D displays have been utilizing the binocular cues for a very long time. Here I'm making a case today that even integral displays have the capability of doing this depth blur in the eyes. Here's an example of integral display where I show how retinal blur or depth blur can be seen with the camera. So camera is focused in the front, background is blurred, camera is focused at the back, front is blurred. So let's see how these integral displays can do this, give this cue of monocular accommodation. So in a real world, when we have a point at a given depth, it emanates rays at different angles, which enter the pupil of the eye and converge on the retina. So from here, from geometry, we can see that for finding out the depth of exact point you're looking at, you need at least 2 rays coming out of the object, so that the retina or so that the lens of the eye can change its focal length to bring that point in focus on the retina. So for example, here's a point in front, here's a point at the back. Eye has to use a longer focal length, eye has to use a shorter focal length to bring it in focus. So the simple conclusion here is that two rays are needed at least at different angles to simulate this change in focal power. So for the integral displays, these two rays actually translates to having two views entering the eye. So here is an example, an enlarged view of human eye and a lenslet array, an integral displays the viewer is seeing. So in this case, we assume that there are three views entering the eye. So what we can see is that as eye has a fixed focal power, one of the objects which is created by these different views, comes in focus on the retina, and the object at a slightly different depth looks blurred or has sparse spots on the retina. So that's how the integral displays simulate accommodation. As we studied these integral displays further, we found out that we can analyze all the depth points which are formed by these integral displays by analyzing two lenses which are adjacent to each other. So the central lens one is centered on the eye, and then we look at one ray from it, and then adjacent lens 2, and we analyze different rays at different angles coming out of it. So what happens is that these rays, as they intersect with the central lens ray, they form different object points at different depths. And what I do is I plot the spot sizes from this ray as the central ray and analyze those. So that's what I do. And how do I simulate the light propagation from these integral displays? So I use this fast Fourier beam propagation method. I use that because it includes diffraction effects from all the optical elements and free space. It's better than just using geometric optics analysis, and because that doesn't give me the spot size or spot information. So here's an example of collimated light coming out of a lenslet, propagating in free space, landing on the pupil, and the eye lens gets focused on the retina. Here's an adjacent lens which sends light off of at a different angle, and then same thing happens. So here's a simple schematic of if I take two rays from lens 1 and lens 2 and plot their spot sizes at different planes. So these are the different planes in this, and then look at these spot sizes. So the green is the pupil plane, the blue is the lenslet plane, and then red and black are the retina plane. So here what I see is that on the pupil, both these rays land on top of each other, or beams land on top of each other. So that means they are coming from the same view, and then they form 2 pixels. So essentially, these 2 rays are forming 2 pixels of the same view. In second case, I change the angle coming out of lens 2 by changing the pixel position on the elemental image. The spots now don't land on top of each other at the pupil plane, but at the retina plane, they are, they're at the borderline of the separation. So I analyze the separation between these 2 spots to find out if the object is in focus or it is out of focus or it has a continuous blur. So here is one of the important results of what I've studied and I plotted is that, so this is one of the key plots. What I'm plotting here is each of the points on this plot represents the spacing between the 2 spots as I showed in the previous slides. So this is a plot of normalized separation between the 2 spots on the retina, and these are out of focus spots. So I'm assuming that the eye has an in-focus spot and an out-of-focus spot landing on the fovea at the same time. An in-focus spot is formed by some other lens and ray combination, and this is just the out-of-focus spot. So each of these points represent that. The y-axis is the focus position of the eye. The eye is located somewhere here. The display is at 300 millimeter. And then eye is able to focus at these different depths. So the x-axis here is the angle, which actually is equivalent to, geometrically equivalent to the pixel position in the elemental image. So the red line here is when the pixel position creates the same view. And then this, what you can see is that the blue points here are when the spots are exactly overlapping. The maroon region is when they are well separated. And the intermediate region is when they are, they are not a single spot, they are a broader spot, but they're not well separated. So one of the major conclusions I drew from this plot is that the depths which are very close to the display here and here have actually only one view entering the eye, even though this example of integral display has 23 views entering the eye. For certain depths, there's only one view entering the eye. So that means you can perceive depth by only stereo. You cannot do it with depth blur. The second conclusion is that the total number of discrete depths for which we can have the retinal blur is actually equivalent to the number of views getting into the pupil. So this is something which I hadn't seen reported before. Integral displays can have many more views equivalent to the number of pixels in the elemental image, but only the number of views which are getting into the pupil can have the depth blur. And then the last conclusion here is that each of those depth points has lesser and lesser views. So here's a plot showing that for each depth position, how many views contribute to form that depth spot. What I see here is even though there are 23 views entering the pupil, only very few, less than 5, are contributing to most of the depths excuse me, I'd be interested in. So the second analysis, what I did is, since it's simulation, I have a power of changing the integral display parameters. So I kept the lenslet same, viewing distance same. I vary the pixel pitch of the screen which I'm using. What that does is changes the number of views in the pupil. So here, and I compare 5 different characteristics, or actually 3 different characteristics. First, I look at the normalized spot separation, which I explained previous slide. Second is the number of views entering the pupil. The third, I actually account for the resolution of the eye. I assume a pixel size of the fovea of about 2.5 micron. We have very sharp resolution there. And then find the absolute spacing between those 2 spots. And then the last 2 columns are actually simulation of blur from this out of focus object from the integral display, and a separate simulation of blur as calculated by this beam propagation method for a real object scene. So what I do now is that I vary, since in the previous slide I had about a very small pixel size, which the display doesn't exist today with 1 micron. It has 120 views entering the pupil. Now I change the pixel size from 5 micron to 10 micron to 20 micron and reduce the number of views entering the pupil. What the first thing we see is that as the number of views are reducing, the number of discrete depth points, these white dots are actually theoretically calculated depth positions. So these depth positions are reducing. So here I have 23, 12, 6. First thing is that if I actually look at the depth of field of the human eye, this reducing in number of views in the pupil is actually not that bad. Because the depth of field of the human eye tells me that if I'm looking at, let's say, 600 millimeter, I have about plus and minus 100 millimeter depth of field of the eye, where I cannot tell the exact depth of the object. So using that ability of the eye, I don't need that many views in the pupil. So, roughly this display can give me enough views behind the display or in the front of display with good enough depth of field. The second conclusion I draw from this analysis is that these are the regions which have continuous blurred spot size. The blue region is in focus. So let's say if my eye is focused at 800 millimeter in this display, one point will be in focus, but there are two other points which will have a continuous blurred spot. It will not have these choppy edges with overlapping, chunky edges. So it'll have a continuous blur. But as I reduce the number of views, I lose that ability. In this case, there's actually all the edges, what I'll see out of focus edges will have a discontinuous edge. So here also about 12 views in this displays is okay, probably. So the third thing I compare is the spacing, absolute spacing between the two spots. This is almost the real world here. And then as I reduce the number of views, it becomes quantized. This is a very good approximation of the real world. This is somewhat quantized, and this is highly quantized. This, as I compare the blur from the real object versus the integral display, I see the same effect, that this is a very good approximation of this plot. This becomes further quantized, and this becomes further quantized. So from, sorry, I'll just do here. So, out of all these observations, what I found is that by keeping the depth of field of the human eye in picture, by keeping the spatial resolution of the eye in picture, roughly 12 views seem to be a good approximation for this integral display. So I ran this simulation for various parameters. So for an integral display, I fixed varied lens pitches from 0.2 millimeter to 1 millimeter, varied f numbers from very short to very long, varied viewing distances, and pupil sizes. And what I found is that in all these cases, heuristically, this approximately 10 views seem to be for a 4 millimeter pupil size, seem to be a good number which can start mimicking the real world, which will have enough in-focus, out-of-focus depth points. More than 20 views is definitely not necessary. So here's a summary of basically all the results I've found is that using this diffraction-based simulation method and keeping the depth of field of the eye and spatial resolution of the eye in picture, integral displays theoretically have the ability of providing this accommodation response or the retinal blur on the eye. The key observation is total number of discrete depths, which can have a blurred spot, is equal to total number of views entering the pupil. And then the last one is that for a 4 mm pupil size in one dimension, 10 views are roughly good enough to start giving you, to actually mimic a real world kind of scenario. 20 views is definitely unnecessary. 2 views are at minimum because it gives you 2 depth planes to focus on and defocus on to start triggering accommodation-like response. So with that, I'll end. Thank you very much.